Can anyone remember where we left off in the last class? How far it was covered in the last class? Anyone? Devraj, are you there? If I don't get any response from your side, I won't start the class. That's for sure.
Sir, up-down counter.
Yeah? Shobik?
Up-down counter.
Okay, that is asynchronous counter, right?
Yes, sir.
Okay, so today we'll start with the concept of synchronous counter or parallel counters. The main two disadvantages or the limitations of asynchronous counters that we found out is that the highest operating frequency for asynchronous counter is limited because of the ripple action in the asynchronous counter. Now, what is meant by ripple action? In asynchronous counter, the flip-flops are excited by the flip-flops in the previous stage, except for the first flip-flop, which is excited by an external clock. Rest of the flip-flops are excited by the transition of the previous or succeeding flip-flop. So the problem is that to change the state of a flip-flop, you need to change the state of a previous flip-flop, which again depends on the change of a state of a flip-flop previous to that. So there will be a ripple effect. That is, first a flip-flop should change its state in requisite way, that is from high to low. Then only the next flip-flop will be affected. And again, only when the transition from high to low of the second flip-flop will the third flip-flop be affected. So this ripple effect, what it does, it increases the settling time for a counter. And this settling time for a counter is approximately equal to the product of the delay time of a single flip-flop multiplied by the total number of flip-flops. That is, the delay time in these flip-flops are in cumulative form. So they increase the total settling time of an asynchronous counter. So that obviously is not a very healthy situation because you cannot have very high operating frequency because of this limitation. Another limitation that you found that when you are trying to connect LEDs to indicate the counting sequence, we observe that some glitches will occur because the output transition from one state to another state is not very smooth in asynchronous counter. First of all, because of the delay time or the propagation delay and this ripple effect. Because each flip-flop has its own delay time before which it cannot respond. So there will be an unwanted states appearing between a recommended state transition. So that will cause a glitch. Now both of these problems can be overcome if all the flip-flops are clocked simultaneously or synchronously. How that can be done? That can be done in a configuration that is called a synchronous counter. Okay. Now, a synchronous counter can be designed for any count sequence. It need not be binary. And it can be designed following a very systematic approach. The only difficulty is that the synchronous counter will have more complicated circuitry as compared to an asynchronous counter. Here in this figure, we see a 4-bit, that is mod 16 synchronous counter. Now, if you look at the figure, you see that the connection diagram, if you look at the connection diagram, these 4 flip-flops, if we term this as A, B, C, and D, they're excited by the same clock pulse. So they're excited by the same clock pulse simultaneously. And the first flip-flop has its T terminal connected to a high. So it will always be 1. But what about the second flip-flop? The second flip-flop T terminal is connected to the output of first flip-flop. The third flip-flop is connected, the T terminal of the third flip-flop is connected to the product or the AND of the input or the output QA and QB. Similarly, D flip-flop, the T input is connected with the AND operation of QA, QB, and QC. So this is how a 4-bit synchronous counter is fabricated. Now let us see how the synchronous operation actually takes place, or the counting operation actually takes place in this particular configuration. For that, we shall consider only a few steps. So let's start with the initial condition. Say initially the clock is at this state 0, which is 0 0 0 0. So the output is 0 0. So this is 0, this is 0. So at this point, this is always 1. So what will be the input to this T terminal? This is 0. Input to this AND gate, 0 and 0. So this will be 0. So to this, obviously 0 0 0. So obviously this will be 0. So at this point a clock appears. Okay, in red. So when the red clock appears, this is the input condition to these flip-flops A, B, C, and D. So what will be the corresponding change in output? See, only the A flip-flop will toggle. So I'll show that in blue. And the rest of them will remain same. So the new control word will be, 0001. And we started from 0 0 0 0. Right? Obviously, this will be your A, B, C, and D. Now, at this point, when the blue output has appeared, what about the input to the T flip-flops? See, this one is 1, so this will become 1. And this 1 multiplied by this 0 will be 0. So again, 1 0 0, it will be 0. So now, at the next stage, this blue, this is corresponding to the output corresponding to the clock that has appeared. This is a red clock. Now after that, the A, B, C, D flip-flop have their inputs marked by blue when the next clock appears, say, which is indicated by green one. So what will happen as soon as this clock appears? This obviously has a high value, so it will toggle to 0. So A will become 0. What about this? Now this has a high value of 1, so output of the B will toggle to 1. But the input of C is 0, so it will not toggle. Input of D is also 0, so it will not toggle. So it will move on to the state 2. 0 0 1 0. If we proceed further, so what is the inputs now? The input to this flip-flop is 0. To this flip-flop is 0. And what about the other flip-flop? This is 0 1. So this is also 0. Right? Now again, what will happen to the next clock pulse when it appears? Say a black, I'm showing the black pulse appears. So this is 1. So this is obviously toggle the state 1, right? What about the flip-flop B? It will remain 1 because it's now 0, so it will remain at 1. Flip-flop C, so this is 0, so this is remain 1. Flip-flop C is 0, so it will remain 0. D's input is 0, so it will again remain 0, right? So the control word will be 0 0 1 1. So it is 0 1 2 3. So in this way, this will act as a counter. Okay, it's an up counter. So this will continue until what point? So this will continue until say the output is now 1 1 1 1. That is 15, right? So it will count from 0 to 15. Then if a clock appears, then what will happen? See, when this is 1, this is 1, this is 1. So this input is 1. This input is 1. This input 1 by 1, 1 and 1 ended 1. So 1 ended 1, ended 1. This is 1. So all of these 3 are 1. So this will be again 1. So all the t inputs will be high. So as soon as this clock appears, what will happen? All of them will toggle to 0, 0, 0, 0. So it will move on to the state 0, and again it will start counting from this sequence. So it will count from 0 to 15. That is, it will go through 16 states, right? So this is why it's called a module 16 or mod 16 counter. Okay. Now, what is the difference between this synchronous counter and asynchronous counter? In this case, the propagation delay, unlike asynchronous counter, where the total propagation delay was the propagation delay due to A, B, C, D added together. In this case, the total propagation delay will be equal to the propagation delay of one flip-flop, say T flip-flop, plus the propagation delay of one AND gate. Why so? Because the time taken by one flip-flop to toggle, this is TF, plus the time for the new logic level to propagate through a single AND gate to reach the T input of the following flip-flop. So as soon as this flip-flop toggles after TF time, so this signal will be propagated through this AND gate to the next T. So this is what will get TG. This is a propagation delay of an AND gate. So total delay will be the propagation delay of an AND gate plus propagation delay of one flip-flop. That is the time for flip-flop to toggle its state. And then the time for the new logic level to propagate through one single AND gate. See, this signal will excite this flip-flop, but it will pass through only one AND gate. These two signals will excite this flip-flop, but it will pass through only one AND gate. So the total delay time will be like this. So maximum frequency will be limited by 1 plus TF plus TG. Right? Obviously, given same number of flip-flops, in this case, the operating frequency, the maximum operating frequency will be much higher as compared to asynchronous counter. For asynchronous counter, it could have been 1 plus n into TF. N is the number of states. Right? So obviously, this will have much faster speed of operation as compared to an asynchronous counter. So this is the main advantage of synchronous counter. But this synchronous counter is called a synchronous counter with parallel carry. That is, the carry is being forwarded in a parallel manner. The problem is that in this case, if you keep on adding stage after stage, what will happen? The number of AND gates will increase. 1, 2, it will require third AND gate, fourth AND gate. Not only that, the number of inputs to this AND gates will also increase. For this third AND gate, how many inputs will be required? It will require 4 inputs. This fourth AND gate, it will require 5 inputs. So that is why it will become much more complicated. The circuit will become much more complicated. So what you can do, you can simply suitably connect these AND gates to obtain another circuit that is called a synchronous counter with ripple carry, where the connection will be something like this. In this case, what is happening? The same logic has been carried out, but what we are doing actually, see, this is your QA, this is QB. So what is this? QA, QB, that is being used to excite C. Now, D should be excited by QA, QB, is this signal with ending operation of QC. So by this configuration, what we have done, we have eliminated the number of extra inputs that you require. It requires 2 AND gates, but only with 2 input AND gate will suffice. We did not have that multiple input AND gates. So if you want to increase the number of stages, what you have to do? You have to just input or include another AND gate with 2 inputs, where one of the inputs will come from the previous stage, another input will come from the flip-flop output of the present state or the previous state. So in this way, you can eliminate the complexity of number of inputs of an AND gate. Now there is a problem or the penalty that you'll pay. What is the compromise? As soon as you keep on increasing the stages, what will happen? The propagation delay with respect to D will be TF plus TG1 plus TG2, because any change in this state to affect this state will have to go through these two AND gates. So similarly, if you have another stage, so it will be just adding the propagation delay through AND gates. So what will happen in general for an nth order counter, the total frequency, the maximum frequency that you can achieve will be given by this, where this is the total delay time, TP being that of the flip-flop, and n minus 2 into TG is being that corresponding to the AND gates, which are now acting in a cumulative manner. So this will obviously restrict the frequency as compared to the parallel carry situation. So that's why it's called a ripple carry. But what you're gaining is a less complex network. Okay, with only two input AND gates that we require now. Right? So this is the synchronous up counter with parallel carry and ripple carry. Now, what about synchronous down counter? We have already seen how asynchronous down counters can be achieved by simply changing the point from where you're taking the output of a T flip-flop to excite the next state. So what we'll do, we'll simply connect, instead of Q bar to the, we'll be using this Q bar to generate the T input for the succeeding or the following flip-flop. So what will happen? This will give rise to a situation where we will get a down counter. Let us see, let us observe. Let us start with initially relaxed system. That is 0, 0, 0, 0. Since this is already 1, so what will be the input to this? Q bar, if it is 0, so this is 1. See, Q bar is 1. What about this? This is 0, so this is 1. This is also 1, so this will be 1 T input. So this is 0, so this will be 1. So again, these two are 1, so this will be 1. So under this condition, if a clock appears, now this red T will correspond to a clock appearing with red. So corresponding to this red clock, what will happen? What is the transition? See, this T has a 1, so it will toggle. This T has a 1, so it will toggle. This T has a 1, so it will toggle. So it will toggle. So it will start from 0, 0, 0, 0. As soon as the red clock appears, it will move on to 1, 1, 1, 1. Now, say a clock appears here. So if it is 1, 1, 1, 1, so what will be the inputs? This is 1, fine. What about this one? If this is 1, so what about Q bar? This is 0. This is 0. This is 0. So if this is 0, what will happen? And this is 0. So this will be 0. This is 0. So these two are all 0. So this will be 0. So at the blue clock pulse, which flip-flops will toggle? Only this flip-flop will toggle. So it will be 0 and rest of them will be same. Right? So this will be the word 14. Now let us see at this condition, another clock appears. This is a negative transition of the clock appears. So under this condition, what are the values? So since this is 0, this has become 0. This is 1. This is 1. This is 1. Since this is 0, so this will be 1. So this means this will be 1. But since this is still 1, so this is again 0. So again, this will be 0. If any one of them is 0 means this will be 0. So this green clock pulse, which will transit, this obviously will move over from 0 to 1. And this is also having a value 1. So this will toggle QB from 1 to 0 and rest will be same. Right? So this will be the word 13. If you now again put a clock, you'll see it will count down to, and this will continue. See? Understood? So in this way, it will act as a synchronous down counter. So we have seen how a synchronous counter can be used, made to use in a count in a up mode, also in a down mode. So what is left is a synchronous up down counter or a multi-mode counter, where it can count both in up direction and also in a downward direction. So that can be achieved by using a simple logic like this, where we have a up down control signal switch, where you can put a value 1 or 0. Depending upon that value, either this Q will be used to excite the T flip-flop of the succeeding stage, or Q bar will be used to excite the T input of the next flip-flop. So we'll get either an up counter or a down counter. Let us see what will happen if we have this value as 1. If you put this value as 1, this will be 1. So whatever value will be there will be transmitted. Right? But if this is 1, what about this? This will be 0. So this, whatever value is there, this will be all forced to 0. So this flip-flop will be excited by the Q state of this flip-flop. Again, this flip-flop will be excited by the Q state of this flip-flop. So what you'll get is basically an up counter. Right? Now, if you give a 0 over here, so what will happen? This will be 0. So this will be nullified. No signal will be passing through it. Again, this will be 0. Okay. So what will happen? This will be 1. So this will be transmitting the signal. Right? So in this case, only the lower AND gates will be acting. So Q bar will be used to excite the T flip-flop of the next stage. So it will be simply a down counter. So in this way, you can decide which of this Q bar to be excited, and based on that, you can have both an up mode, counting mode, and down counting mode embedded in a single configuration. That's why it's called a multi-mode counter, with the facility of both counting up and counting down, which can be controlled by simply putting 1 or 0 in this count up or down control signal input. Okay. Next, we shall consider what is called a synchronous asynchronous counter. That is a counter that combines both the advantages of synchronous counter and asynchronous counter. If you look at the configuration, this is a special type of counter. This is found by combining the synchronous and asynchronous counter. So obviously, they carry both the advantages of synchronous and asynchronous counter as well as the demerits of synchronous and asynchronous counter. If you look at the counter configuration, see, there are 4 stages or 4 flip-flops. Say, sorry, I think blue will not be very much visible, so I'll put red over here. A0, A1, A2, and A3. See, this A0 and A2, they have their J and K both put to high. And A0 is excited by the external clock. This is only flip-flop that is excited by an external clock. Right? Whereas this A2 is excited by the output of this A1. So you can say A0 and A2, they form an asynchronous connection. See, because in this case, JK are high, so their transition will depend only on the negative clock pulses. This case also J and K high. So the transition or the toggle mode will be dependent upon only the clock pulse. That is nothing but the state transition of the output of A1 flip-flop. So they are connected somewhat in asynchronous manner. Whereas the other two flip-flops, that is A1 and A3, they change their state simultaneously based on the clock transition from high to low, or the not clock transition, the output transition of high to low of the flip-flop A0. So what will happen? A1 and A3 will change their state simultaneously if they are in a favorable condition, depending upon the state of J and K, because they are being clocked simultaneously or synchronously. So A and 3 will form the synchronous part. So A0 and A2 are forming the asynchronous part, and A1 and A3 are forming the synchronous part of this synchronous asynchronous counter. And this is nothing but a BCD counter, binary coded decimal counter. Now we'll examine how this counter as a whole will operate. Have you understood this? How this is A0 and A2 are asynchronous and A1 and A3 are behaving like a synchronous counter? Okay, since no one is responding, I guess you have understood this. Now let us consider the principle of operation, how this counter is actually operating. So to start with, let us start with a very basic state, that is the state 0000. So under this condition, see the main conditions that are to be mentioned here, that J and K are high for A0 and A2, but K for all the flip-flops are high. They are connected to VCC, right? Now the clock input is only given to A0, and since J and K are both high, so for each clock transition, this output A0 will toggle 0, 1, 0, 1, 0, 1. Whereas A1 will only toggle when this transition of A0 takes place from 1 to 0 on negative edge. And this will not toggle, this will change the state of A1, but the state of the A1 will depend upon the value of J. If J is 0, it will be reset. If J is 1, it will then toggle. Okay. Similarly, A2 will be clocked by the output A1, but since J and K are both high, so the A2 will simply toggle based on the lower transition of A1. But A3 will have its input J, which is a combination of A1 and A2, or ANDed with A2. Okay, so these are the conditions that we should always remember. Now, when the state is 0000 and a clock has appeared, so what will happen? This clock will cause this state to change to 1. Okay. So this will be simply, I should write the word for us. To start with, we have a word 0000. As soon as the clock appears, it will be 0001. Right? So this will just start counting from 0000 and it will move over to 0001. This is at the first clock pulse. Now, under this condition, these are all zeros. Why? See, this will have a transition 0 to 1, so this will not be excited because this is a rising edge. Similarly, this will be a rising edge. So this A1 and A3 will not be excited. So if A1 and A1 doesn't change its state, then A2 will not be affected. So this will not toggle, or no change of state will happen for A1, A2 and A3. Now at this point, if a clock pulse appears, then what will happen? This will move over to 0. So clock like green will appear, because A0 has now moved from 1 to 0. So this will excite this. But what is the value of J with respect to A1 now? With respect to A1, J is 1 because this is 0. So that means this is 1. Sorry, I should be writing this using color blue because the clock is blue. So when this is 0, so this is 1. So this 1 will appear over here, right? And due to this blue clock, what will happen? State change 1, 0. So there will be 2 clocks appearing here. So for this A1, we have J equal to 1, K equal to 1. And there is a negative clock. So it will toggle to value 1. What about A2? This clock gives rise to this sort of signal. So it is not affecting A2, so it will remain 0. Again, in this case, what about A1 into A2? So J will be 0. So it will not change its state. It will remain in a reset condition. 1 second, I'm having a call now. Just a second. Okay, sorry for the interruption. So where we were? So we have been looking at the transition. The blue is a current state where a clock has appeared, and green gives you the transition of the states, right? So the new word that you'll get will obviously be in green. Sorry, it's a pain. 0, it will remain 0 because since this is 0, although there is a negative clock appeared, trailing edge has appeared, but J is equal to 0, K equal to 1 means it will remain 0. So it is remaining 0. For A2, this is 1, 1, but there's only a rising edge, so it will not be affected, so it will remain 0. What about A1? A1 will toggle because of this falling edge, and there's a 1 and J, so A1 will toggle to 1, and obviously A0 will toggle to 0. So this will be the word, obviously 0, 1, 2. Now let us see what will happen if I apply a clock here. I will draw the initial conditions using this green, so that when the green clock appears, the initial condition, what are the initial conditions over here? This is again 0, so that means this will be 1. Okay, so this is 1, but this, what about this A0? A0 is 0. Fine. So this is over here. Any input that you require? No. Fine. A1, A2 is still A1, A2 is 0. So it is now still in 0 condition. So with this, a clock has appeared. So what will be the transition? First of all, since this will again be toggling to 1, this toggle will give you a pulse like this. This will not affect A1, so A1 remain 1. What about A2? Since A1 is not changing, it will not change. Again, this will not change. So your control word will be, sorry, this should be 0. So what will be control word? 0, 0, 1, 1. Right? So this is how it will continue 0, 1, 2, 3. If another clock appears, then it will move on to 4 and so on. Now, how long will it will continue? So let us see a special case. I'll remove all these things. That is when the state is 0, 1, 1, 1. That is 0, 1, 1, 1. This is the current state. So what is the AND output? See, A1 is 1, A2 is 1. So this is 1. Right? Now a clock has appeared. So what will happen? There will be transition of A1 to 0. So this will give you a trailing edge at the input of A1 and a trailing edge at the input of A3. So A1 will get an excitation. So what about the input to A1? Since this is 0, obviously this is 1. So this is also 1. So these two are 1. So it is 1 and there's a trailing edge, so it will toggle to 0. But what about A2? Since A1 is toggling from 1 to 0, it will provide a clock like this. So this will cause A2 to move from 1 to 0. Right? So this will become 0. What about this A3? Now this clock pulse has appeared. This is 1. So this is high. K is already 1. So this will make it to toggle. So the new word will be 1, 0, 0, 0. So it was 7. Now it moves on to 8. Right? Now let us see what happens if a clock appears now. So under this new state, since this is now 1, what about this? This has become 0. So this has become 0. Right? This is the only thing that you can remember. But A1 and A2, they're both 0. So what about this? So this is 0, this is 0. So this has now become 0. So the blue clock has appeared where the J input of A1 is 0 and J input of A3 is 0. So let's see how the things will change. What about A0? It will become high, obviously. So this will give you a pulse like this. So this will obviously not excite this A1, so it will remain 0. Since A1 is remaining 0, A2 will not be excited, it will be 0. Since this is a high pulse or a rising edge, so this will not excite A3, so it will remain 1. So the control word will be 1, 0, 0, 1. Right? This is 9. So at this point, the clock has appeared. Right? This is very, very critical. See, at this point, what are the other values? Since this is at 1, so this is remaining 0. So this is J input is 0. A1, A2 both are 0. So J input is again 0. Right? So now the clock has appeared. Green clock has appeared. So what will happen? It will toggle this to 0. Right? If it toggles to 0, then what will happen? This will generate to trailing edges or the falling edges. Now this falling edge will excite this. But what is the input to this? 0. J is equal to 0. So this K is equal to 1, fine. But since J is equal to 0, it will not change its state. Right? Since it is not changing its state, A2 will not change its state. Right? What about this? A3. Now A3 has a clock like this. But input to A3 is 0, J equal to 0, K equal to 1. With this, a clock has appeared. So what will be the condition? It will obviously be moving on to the reset condition. So it will now toggle to reset. So at this point, after this green clock, it will move on to 0, 0, 0, 0. See whether you've understood this or not. So it will again get back to the 0, 0, 0, 0 state, 0 state, and on consequent clock, it will again count from 0, 1, 2, so up to 9 it will count, then again it will become 0. So it will be a BCT counter. That is count up to 10 only. Okay, it's clear? Or any doubt you have? Can you be please louder? One second. Was there anybody who's asking any question? দেবরাজ ঠিক আছে?
Yes, sir, it is okay.
ওকে ওকে ঠিক আছে ঠিক আছে না আমি কোনো রেসপন্স পাচ্ছি না বলে বুঝতে পারছি না whether you are understanding or not. Okay. Now what I will recommend to understand this, you make or prepare a chart like this. Okay, I'll just give you the outline, then you make a chart like this. See, in this first line there will be clock, then you'll have your output like A3, A2, A1, A0, and then you have your inputs like A3, J and K, A2, J and K, A1, J and K, and A0, J and K. Right? So now what you have now, since given this configuration for A2 and A0, J and K are always 1 and K values are always 1. So the only changes that will appear will here 0 or 1, 0 or 1. What are the conditions that you have? But the conditions that you have is that if you look at the figure, that this J of A3 is equal to A1 multiplied by 2 and J A1 equal to Q A3 bar. And for the rest of the cases, these are all fixed. So J of A1 since this is A1, if you mark this as A1, will be Q A3 bar. Sorry, I should write Q. And J of A3 will be QA2 with ended with QA1. So these are the two conditions that you have. So just incorporate these two conditions with this table and start from say 0, 0, 0, 0, and you'll move up to 1, 0, 0, 1, and again you'll get to 0, 0, 0, 0. So make this table as per your own convenience, just to see how this transition is actually taking place and whether it is counting in a BCD manner or not, right? Next, we shall consider a special type of counter that is called a programmable counter. We shall just consider the schematic of the programmable counter. This is also called a presettable counter, because so far we have seen that up counters and down counters are there. And up counters, we have seen that it can start from 0, 0, 0, 0 and reaches a value 1, 1, 1, 1. Or what you can do at most for mod less than 2 to the power n counters, you can stop intermittently at some value. But the starting point has always been 0, 0, 0, 0. Similarly, for down counter, the starting point has always been 1, 1, 1, 1. And then what we have done, we have counted down from 1, 1, 1, 1 to 0, 0, 0, 0 or to a predefined value. But what we propose here in a presettable counter is that it can be made to start counting from any desired state. You can start from any desired state. For up counter, it should not be 0, 0, 0, 0. Similarly, for down counter, it should not be 1, 1, 1, 1. What you can do, you can program the counter. And how that can be done? That can be done by using a configuration like this, where if you look closely, we have these 4 signals, PA, PB, PC, and PD. These are used to program this A, B, C, and D flip-flops. Now, how they are being programmed? They are programmed by putting a corresponding value as you require to the preset or clear button, or the preset and clear control signals of these flip-flops. So by putting an appropriate value in PA, PB, PC, PD, you can either preset a flip-flop or clear a flip-flop. And thus, you can achieve a desired word or desired state from which you want to start counting, either in an up count mode or in a down count mode. Okay. Now, this preset inputs, that is PA, PB, PC, PD, the value which are already being defined are transferred into the counter, that is ABCD flip-flop, when this preset load is set to low. And then this momentary pulse in this preset load, what it causes, say this is 1, you momentarily make it low and then put it high again. When it is high, it counts in the normal fashion. But as soon as you put it low, what happens? This 4 PA, PB, PCD, PC, and PD, they'll come into the picture. And this NAND gates, all the NAND gates are now activated. As soon as this comes into the picture, the ABCD flip-flops will be either preset or clear, depending upon the choice of your word. And after this duration, after a small duration, if you want to put to it high level, then it will start counting either in up or down count. This is up counter. So it will start counting from the value you have preset. So this is how you can program a counter to count from a predefined value. Right? So this is why it's called a presettable or programmable counter. Okay. So in this way, we have seen the various types of synchronous counter. Okay. Now what we'll do, we'll see how you can design a synchronous counter. Given a specification, how to design a synchronous counter. We'll just briefly discuss that topic. And that will be the concluding part here. So the design procedure will follow the following step. So given the word description of the problem, what you have to do, you have to draw a state diagram. So I have not yet discussed about the state diagram. I'll give you just a hint about that, because in the next class, when we will be discussing about sequential systems in general, I shall consider the concept of state diagram. Then from this state diagram, it will describe the operation of the counter. Now, from the state table, write the corresponding count sequence to form a table. Then you have to find out the number of flip-flops that will be required to obtain the count sequence. Finally, decide the type of flip-flop that you want to use, JK, T, SR, D, whatever. Then you have to prepare the kernel map for each flip-flop in terms of flip-flop outputs at input variables, and then simplify the kernel map to obtain the final connection diagram. So, as we have discussed already in interconversion of flip-flops, the steps are almost similar. So, suppose we are intended to design a counter, synchronous counter, which has a modulus less than 2 to the power n. That is, it's not counting to the full capacity of the counter. Rather, it is keeping 1 or 2 states. Okay, because for a counter of n flip-flops, the natural count is 2 to the power n. But we are not counting up to 2 to the power n states. Rather, we are counting a state less than that. Now, what does that mean? If you have a 2-bit, 4-bit, 3-bit counter, what does this mean? For a 2-bit counter, it will consist of 2 flip-flops, 2 to the power 2 equal to 4. So, it will go through 4 states. For a single flip-flop, it will have only 2 bits or 2 states, 0 and 1. For 3 flip-flops, there will be 8 possible states that it can be. So, given a number of states that you want to count, if it is in the form of 2, 4, 8, 16, so on, you can directly design by using 2, 4, 3, 4 number of flip-flops. But if you want to have a counter with a modulus other than 2, 4, 6, 8, suppose 3, 5, 10, then what you have to do, you have to eliminate some of the steps, or you have to ignore some of the states, so that such counter will be not utilizing the full states available. That is why you call that type of count a modified count, where some of the states are skipped intentionally, because you want to count only a few steps, not all the steps that a counter can count. So let us see, for example, we want to design a mod 3 counter. That is, it should have 3 states. Now, for mod 3 counter, what are the desired states? There is 3 states. So we know to obtain a 2-state counter, we require 1 flip-flop. To obtain a 4-state counter, we require 2 flip-flops. To obtain a 3-state counter, then how you can determine the number of flip-flops? That can be determined using the formula. This formula is 2 to the power of n minus 1 is less than capital N, less than 2 to the power n, n. Where n is the number of flip-flops that you require. Now, in this case, your capital N is equal to 3. So, what will be the value of n? It will be 2. So, what you require for this mod 3 counter is 2 flip-flops. Now, you can choose any flip-flop, JK, SR. So, for the purpose of simplicity, what we will do, we will choose only T flip-flop, right? So, let us see how the possible state transitions are. Now, what do you mean by state transition? If you look at this state diagram, I'll discuss about the definition of state diagram in the next class. What it does is a pictorial representation of the states of the clock. So, what are the transition of the clock? 0, 0, 0, 1, 1, 0, then it runs back to here. So, if it is in a state 0, 0, at the next clock pulse, it will move over to state 0, 1. So, if the present state is 0, 0, the next state should be 0, 1. If the present state is now 0, 1, what will be the next state? It should be 1, 0. The present state is 1, 0, then the next state should be 0, 0. So, in this way, this table, this is called a state table, where you have the present state and the next state. This can be represented in a pictorial form that is called a state diagram. See, this is the present state. If it is this present state, at the next clock pulse, it should move to this state. This is next state. Now, this becomes the present state. So, at the next clock pulse, it should move over to this. So, this is how a state diagram is depicted. So, this is also the corresponding state table. Now, what we have to do, we have to obtain the excitation table, so that this state transition actually happens. Since we're using two T flip-flops, say A1 and A0, so let us see the count sequence. So for the first state, say the present state is 0, 0. So what you require is that at the next clock pulse, the output should change over from 0, 0 to 0, 1. So if it has to change to 0, 1, then A1 should not change. So what would be the input to the flip-flop A1, T flip-flop A1? It should be 0, so that it holds on to the current state. But A0 should change its state from 0 to 1. So the T input of the A0 should be connected to a high value, or it should have a value high, 1, so that at the next clock pulse, it toggles from 0, 0 to 0, 1. So this corresponds to this excitation table. Now it is at 0, 1 state, 0, 1 state. So what is the desired next state? 1, 0. See, in this case, A1 toggles from 0 to 1 and A0 toggles from 1 to 0. So therefore, both the T flip-flops should have 1 as their input, so that they both can toggle from 0 to 1 and 1 to 0 respectively. So this is the required value of control input. I said input to the T flip-flops, T inputs. Now from 1, 0, what is the next state? 0, 0. So in this case, A0 should 1, 0 to 0, 0. If it is now in 1, 0 state, because it's moved from 0, 1 to 1, 0. So this A1 should now toggle from 1 to 0. So the input TA1 should be 1, but A0 is remaining at 0. So it should be 0. So this is the required set of inputs that you require so that this operation can take place. Okay, this sequence of operation can take place from 0, 0 to 0, 1, from 0, 1 to 1, 0, from 1, 0 to 0, 0. As soon as it reaches 0, 0, after this third clock, it will again start from this point. So this input corresponds to this state change, this input corresponds to this state change, and the third set of input corresponds to this state change. So this is how you develop the excitation table corresponding to this state change, which is depicted by this state diagram or this state table. Now let's see what should be the corresponding configuration. If you now draw the Karnaugh map for this counter, I should zoom out a bit. Is it visible, the Karnaugh map?
Yes, sir. Yes.
So corresponding to this TA1, this is for TA1. If you have two inputs, A1 and A0, so 0, 1, 0, 1. So when A1 equal to 0 and A0 equal to 0, what is TA1? 0. When A1 equal to 0, A0 equal to 1, what is TA1? 1. When A1 equal to 1, A0 equal to 0, what is the value? 1. And for both of them, since A1 and A0, they never become 1 simultaneously, so this will be a don't care state. So obviously, if you now consider this Karnaugh map, your word or the logic for TA1 would be A1 plus A0. Similarly, for TA0, we'll have a Karnaugh map like this. So for this, you will get TA0 equal to A1 dash. So this will be the Karnaugh maps for TA1 and TA0. So if you put into this logic diagram, what you will have? This is your A1, this is A0. This is a synchronous counter. The clock is common to both of them. and you have count outputs A0 and A1 over here. So T A0 will be A1 dash, so you have to connect Q bar A1 to the T flip flop input of A0, and this T A1 will be nothing but A1 plus A0, so it's the ORing of this. So this will be the logic diagram of a mod 3 binary counter. And you can show that it will count from 0 0, then to 0 1, then 1 0, then again back to 0 0. Okay, that can be easily shown. So this is how you can design a synchronous counter, obviously with modulus less than what we have normally, using this Carnot map and things like this, right? So in this way we have covered asynchronous counter and synchronous counter, right? We have seen up and down asynchronous and synchronous counters. We have seen the asynchronous synchronous counter in a combined mode where you have both the functions of synchronous and asynchronous counter. And finally, you have a presettable counter or a programmable counter where you can start up and down count from any predefined value, right? So with this, I will conclude today's lecture. In the next class, we shall consider and shall start with the concept of sequential system and types of sequential systems, right? So any question regarding today's class? Shomadip Roy, are you there? Shomadip Das, sorry. Yes. You had some confusion regarding this asynchronous and synchronous counterpart. Can you be more specific? Which part you didn't get?
স্যার দুটো কাউন্টার সিনক্রোনাস আছে আর দুটো কাউন্টার অ্যাসিনক্রোনাস আছে, তো ওই জায়গাটা থেকে আমি
আরেকবার বলো।
দুটো কাউন্টার সিনক্রোনাস ছিল আর দুটো কাউন্টার অ্যাসিনক্রোনাস ছিল, তো ওটা কিভাবে হচ্ছে আরেকটু।
আচ্ছা, ওকে, sure. See, in this case, this A0 and A2, see, this A0 is excited by an external clock and their J and K are always high. So whenever the clock transition happens like this for a trailing edge or a falling edge, the output Q will simply toggle, okay, between 0 and 1. Similarly, for this case, since J and K are both high, its output will toggle between 0 and 1. But the clock to this A0 and clock to this A2 are not simultaneous. Rather, the clock to this A2 will be a delayed clock because it depends on the transition of QA1 from 1 to 0, so that it gives you a pulse in the falling edge or the falling edge of the pulse. So what will happen as soon as this transition takes place, say from 1 to 0, this will excite this. So there may be two changes from 0 to 1 or from 1 to 0. For this 0 to 1 change, there will be no effect on A2. But when this A1 changes from 1 to 0, then only this will change. So this clock will propagate through this JK flip-flop to this flip-flop. And depending upon this output, only then this A2 will change. So there will be a ripple effect. See? This ripple effect will transmit from A0 to A1 to A2. So this A0 and A2 combination will obviously be working as asynchronous mode because their clocks are not synchronized. There is a ripple effect. Whereas in the other hand, if you look at A1 and A3, their clock are supplied by the output of A0. So whenever A0 goes through a change from 1 to 0, both of them will be excited simultaneously or in synchronism. That's why you can say that A1 and A3 will effectively be in synchronism. So they'll act as if they're a part of a synchronous counter. বোঝা গেল এবার? কারণ দেখো,
হ্যাঁ স্যার,
obviously their state will depend upon the relative or the current value of J and K for A1 and A3. But when they are in favorable state, favorable input J and K are there, they'll change simultaneously. Okay, so their transition takes place in synchronism. That is why you can say these are working, A1 and A3 are working in synchronism, and their transition is being controlled by the falling edge of A0 simultaneously. That's why they are forming the synchronous part, whereas A0 and A2 are having a ripple effect between them. So they are forming the asynchronous part. ঠিক আছে?
হ্যাঁ স্যার, ঠিক আছে, থ্যাংক ইউ।
ওকে, আর কারো কোনো ডাউট? ঠিক আছে, ধরে নিচ্ছি তাহলে সবাই মোটামুটি বুঝেছো। সো নেক্সট দিন আমরা তাহলে সিকোয়েন্সিয়াল সিস্টেমস ইন জেনারেল ডিসকাস করতে শুরু করবো। ওকে।